in a little bit more detail, what brane worlds are. And the basic idea here is that, as has been mentioned a number of times in various talks, general relativity does break down at high enough energies. And since the universe is expanding into the future and getting cooler, if we run it backwards in time, it's getting hotter and hotter, and the energy, therefore, is going up. So we know that at some time in the early universe, we're going to reach energies where Einstein's theory breaks down. And we're going to need a quantum gravity theory to account for what's happening then. I have a schematic here which shows us running backwards from the current universe at about 14 billion years, where we have large-scale structure well formed and developed, back to that surface of last scattering that's been described in various talks at about 380,000 years after the Big Bang. We spoke about inflation previously, and inflation itself is beginning to probe energies beyond GR's capacities, and certainly before inflation, when we reach the Planck time and earlier times, we know that general relativity is not any longer valid. Now, the problem is, as you well know, there isn't yet any quantum gravity theory that is by any means successful. There are only some promising indications. And in particular, M-theory, which is an incomplete theory that has arisen on the basis of string theories. I'll say a bit more about it later. But M-theory seems to be the favored candidate for quantum gravity, although not everybody agrees with that. You should be aware of other alternatives. In particular, there's the loop quantum gravity program, which is a different way to try to quantize gravity. But it's probably fair to say that M-theory is more widely considered to be a promising candidate quantum gravity theory. It still has a long way to go, though, to prove itself. Now, one of the key things about M-theory is that space-time has more than 4 dimensions. And this is an inescapable feature of the theory. I'll say something more about it just now. But you know about branes from talks by Jim Gates, and you've heard about superstring theory, so I needn't start right from the beginning. You're already aware of these things, I'm sure. One of the key features in M-theory is the existence of these D branes. These strings are branes are one-dimensional objects, and branes are higher dimensional objects, 2 branes, 3 branes, and so on. These are higher dimensional objects which are fundamental in the theory. And the extra dimensions that are in addition to the 4 that we observe and experience can actually be large. Now, when I say large, I mean of the order of a millimeter. That's massive compared to the Planck length, although it's small compared to our notion of large. So you can have large extra dimensions. And another revolutionary feature that emerges in these brane contexts is that the true Planck scale, in other words, the true energy scale of gravity, can be much lower than 10 to the 19 GeV. I'll just pause for a minute there to point out to you that there's what's called a hierarchy problem in particle physics. And that problem is essentially the fact that between the electroweak energy scale, which is about 1 TeV or 1,000 GeV, it's actually a little bit less. Between the electroweak energy scale and the Planck scale is a huge desert. Planck scale is 10 to the 16 TeV or 10 to the 19 GeV. And this huge gap between the fundamental scales of gravity and the electroweak scale is a bother and a worrisome feature to particle physics. And one of the things that brane worlds do is they actually lower the Planck scale. They make it smaller than that. They can bring it right down close to the electroweak scale in some models. And so that could have beneficial byproducts in the sense of solving this hierarchy problem. Okay, so that's essentially the motivation.
Does string theory involve large extra dimensions, or is it just the Braneworld one?
String theory does, yes. It certainly does. I mean, the brane worlds come from string theory. I'll say a bit more about their relation to string theory now, actually, on the second slide. You've had a lot of talks on standard cosmology, both popular and more technical, and we know that it has two sort of contradictory features to it. On the one hand, it's highly successful, but on the other hand, it lacks certain fundamental support in the sense that it has deep puzzles which remain unresolved at the level of a fundamental theory. So although we've got these wonderful observational advances, this is the microwave background sky in a three-dimensional plot as seen by the NASA's WMAP satellite, whose data was released in February last year rather. And here is a schematic of the CMB anisotropies showing just how well the data from WMAP is fitting the theoretical curve. This is a major triumph of 20th and 21st century physics. But as has been discussed in a number of different ways over the past few weeks, the standard model suffers from some deep puzzles. And the key two that I in particular have identified, and others as well, is the fact that we don't yet know how inflation may have occurred and what the field is that may have driven inflation, and we also don't know what the dark energy is that I was discussing yesterday. In fact, you could also say there's a puzzle about dark matter. We don't yet know what the dark matter is, and it's generally believed that that's a more manageable problem, and we're about to find out what the dark matter is. But there may be some more surprises in store for us in that as well. So we have this situation, and in some senses, you could think that what is happening is that cosmology is running into the limits of general relativity, that some of these puzzles probably need quantum gravity to resolve them. But as I said, we don't have quantum gravity yet to do that for us. So what we have to do is we have to start looking at some of the quantum gravity type effects that are suggested by theories like M-theory and see what they tell us about cosmology. And we would hope that in doing this, we're going to gain some better understanding of some of these puzzling aspects that still face us. For example, we might, by looking at quantum ideas coming from M-theory, we might begin to understand what inflation is, or if it's not inflation, something else that has similar properties to inflation. We might hope more ambitiously that we could solve the dark energy problem. Yesterday I was asked a question about the anomalously low quadrupole in the CMB anisotropies. If that is a fundamental feature of the universe, then we may hope that quantum gravity type ideas will explain that loss of power on the larger scales. And a number of other puzzles which already exist, and puzzles which undoubtedly are going to emerge from future observational surveys. Physics is always full of surprises. At the same time, if we start applying quantum gravity type ideas to the study of the early universe, and also the late universe in some cases, we would hope to come up with some new features that can be predicted and that observations can be directed to search for. So there are a lot of reasons to look at quantum gravity effects in cosmology. The problem, of course, is that quantum gravity as a theory is still in its infancy. M-theory itself, as I've mentioned, has made some dramatic progress, but it's more in the mathematical structure of the theory and the actual applicability of the theory to physics and to cosmology. There's been some fairly slow movement. And brane worlds are models that have arisen in the framework of M-theory, and we can take the phenomenology of these brane world models. They're not proper M-theoretic models, they're the ones that we deal with in cosmology, but they take some of the ideas from M-theory, which is believed to be a fundamental theory, and we'll run away with these phenomenological ideas and see what they mean for cosmology. So essentially, we have a choice between us. We either say, look, there's no quantum gravity, we'll just do GR, and we'll forget about anything that is probing energies which are outside of GR's power. And the other option would be to say, okay, quantum gravity is ticking over, it's coming along, we've got some nice ideas coming out of M-theory, so we'll take those ideas and construct a phenomenology and see what it tells us about cosmology. And that's the idea behind brane world models. So in relation to the earlier question there, brane worlds do arise in M-theory, but the ones that we use in cosmology are not strict M-theory models. They're not superstring solutions or M-theory solutions. but they share many of the features that the more artificial brain world models that are exact solutions have. And let me go on to discuss a little bit what those might be. Before I do that, though, I just wanted to highlight two particular things. Maybe it's a bit of a repetition, but it's a way of saying it from another point of view. There are probably two key aspects, in summary, that are involved in this enterprise, this idea of using M-theory ideas in cosmology. The one is that we will hope that the new features brought from brain world theories will give us new understanding. Now, I've mentioned some of these things, which I'm not going to have time to go into. They're moduli fields, which are essentially fields which convey the effect of the extra dimensions on our four-dimensional world. There's exciting ideas like holography, which was discussed by Don Marolf in the first week. This idea that the behavior of gravity in a higher dimensional space can be tracked by the behavior of quantum fields on the boundary of that space. Very exciting idea. And there are many other ideas which are new in the context of general relativity and which may bring some solutions and exciting new aspects into cosmology. And the second aspect is that we can run this the other way around. Instead of saying, okay, what can quantum gravity tell us about the universe, we can say, what can observations tell us about quantum gravity? Because we have these wonderful observations which are getting ever more accurate, ever more detailed, flying satellites to map the temperature of the sky, the CMB, having the automated all-sky surveys of galaxies through their redshifts. So here I've got the Sloan Digital Sky Survey, some of its initial results here. Mapping is due to map the redshifts of 1 million galaxies automatically. And here are the actual data points from various CMB anisotropy experiments showing just how detailed and accurate we're getting. These then become tools for us to actually put constraints on quantum gravity theory. So as the theorists are working away to try and come up with quantum gravity, so observational cosmology can also be saying, okay, hang on, the universe is telling us that theory of yours is either wrong or that parameter that you've introduced has got to be constrained to be this small or whatever. So this other aspect, the other running an argument the other way around is just as important, that we can use what we call precision cosmology to put limits on theoretical ideas, and particular ideas coming from M-theory. In a little bit more detail, you can do this in three different ways, roughly speaking. First of all, by the dynamics of the universe. If you run through the history of the universe, looking at some key events in the history of the universe, one of the most important is Big Bang nucleosynthesis, which happens about 1 minute after the Big Bang, and it provides very tight constraints on any modifications to general relativity. So any theory which messes too much with Einstein's theory at that time at energies of about 1 MeV is going to be ruled out by what we already know about Big Bang nucleosynthesis. The supernovae, which were discussed yesterday, and their redshifts and how they are measured, that will also provide constraints on theories which modify Einstein's theory. Of course, the actual precision cosmology itself involves the large-scale structure, which I've just mentioned, the galaxies and the CMB. And then in the future, we're hoping that gravity wave observatories are going to start detecting gravitational waves and eventually detecting cosmological gravitational waves. And this, as George Ellis explained in one of his talks, would give us a probe even further back into the universe than the surface of last scattering. Because remember, gravitational waves move through matter, all matter is transparent to them, so they would take us way back to the Planck time. But that is in the future. We don't yet have such gravitational wave observations. We're far from them. Now, in the rest of the talk, I really want to spend the time trying to explain qualitatively some of the key ideas in these brain world models. The first question that any skeptical physicist should ask is, okay, this theory talks about these extra dimensions. Why don't we see them? Why don't we experience them? Why don't we bump into them? Why do we believe our world is 1 + 3 dimensional? If you say there's extra dimensions, how come we haven't come across them? Well, way back in the 20s, Kaluza and Klein, two different physicists, came up with 5-dimensional variation on Einstein's theory in which the extra dimension was actually used to explain electromagnetism. And on that basis, a series of models with more than 5 dimensions was built up in the 70s and the 80s. And the conventional idea was that the only way you could that you could have extra dimensions was if they were extremely small. So when I say small, I mean of the order of the Planck length, 10 to the minus 33 centimeters. If the extra dimensions, there might be more than one of them, but if they're that small, this simply means that you would need energies of the order of the Planck scale, which is way beyond accelerators or anything we have, way beyond supernovae and everything except the very early universe, in order to probe those extra dimensions. Otherwise, you wouldn't see them because they were so tiny that particles would have to have unbelievably large energies to actually reveal to you the existence of those extra dimensions. So that was the reason that we didn't see the extra dimensions in these theories. And essentially, that was the case up until the 90s. In the 90s, it was realized through developments in string theory, and I can't go into this, but you must have had some talks about brains. I know you have had some talks about brains. You must remember some of the things that were told to you. But essentially, in the 90s, it was realized in string theory, or superstring theory more precisely, that not only were strings fundamental, but also these higher dimensional objects, the brains. And in particular, D brains are brains which have the property that matter fields, standard model matter fields and gauge interactions, are restricted to these D brains, or if you like, I'll have a diagram shortly, but essentially, as you know, there are 2 different kinds of strings, the open ones and the closed ones. And the open ones have their ends attached to D brains. And they represent photons, standard model particles, photons, baryons, cold dark matter, whatever. Whereas gravity is represented by closed strings which are not attached to D brains. So gravity can access the extra dimensions, whereas ordinary matter may be confined to a lower dimensional surface. And because of this feature, it turns out that it's possible to have the extra dimension being large relative to the Planck length. So this could be much larger than 10 to the minus 33 centimeters. I'll explain a bit more later on how that works. The key idea then of these Braneworld models, which emerge in the context of superstring theory and M-theory, is contained here on this diagram on this slide. So there are 2 aspects. The one is that matter is bound to a lower dimensional surface, which we will think of as our observable 4-dimensional universe. And the second is that the extra dimensions, which are inaccessible to matter, are freely accessible to gravity. So gravity feels the extra dimensions, but matter doesn't directly probe them. And this means that the extra dimensions make themselves felt to us, because we are made of matter, make themselves felt to us indirectly. And we have to try to see them indirectly through the anomalous behavior of gravity. Somehow the higher dimensional behavior of the gravitational field needs to be observable or constrained by observations. That's the basic idea then of the Braneworld model or the Braneworld picture. So the Braneworld is the idea that you have, for example, 2 particles colliding and then producing 2 constituents. This is the space-time picture of a collision. These are standard model particles, so they're stuck to the brain before collision, and their constituents after collision remain stuck to the brain, but some of the energy might leak off in terms of gravitational waves. So the brain world is this 4-dimensional surface, 1 plus 3-dimensional surface, and the extra dimension or dimensions, there could be more than one extra dimension, they are inaccessible to particles but freely accessible to gravity. So that is really the key idea about Braneworld models. To be a little bit more precise about it, in the late 90s or sort of mid to late 90s, a particular set of M-theory models of this kind here in this schematic were discovered, and they consisted of the following setup. You had 2 D branes of 1 plus 3 dimensions at the ends of the world, if you like, at opposite ends of the world. The dimension, the extra dimension that connected these two D branes was large relative to could be large relative to the Planck scale. You could think of these branes as one being our visible brane, the brane in which observers and standard model fields are confined, represented by these open strings whose ends are stuck to the brane. And the other brane is some shadow brane which may have another kind of shadow matter on it or may be empty, depending on the scenario. Gravity obviously accesses this extra dimension, so we have these closed strings freely able to move in the extra dimension. And then it turns out that the remaining 6 dimensions in M-theory, M-theory, as you know from previous talks, is an 11-dimensional theory. The remaining 6 dimensions are compactified on a particular kind of space whose dimensions are small relative to this large extra dimension. And for most energies above the scale of this tiny compactification, you can ignore those extra dimensions, those 6 extra dimensions. But as you go back early enough in time in the universe and get to higher and higher energies, you have to take account of the effect of these further 6 extra dimensions, and thus will be felt on the universe, on the observable visible brane, through what I mentioned earlier, namely the moduli fields. But I'm not going to go into that. That's a kind of extra complication. The basic idea here is that for large parts of the history of the universe, one can treat the universe as effectively 5-dimensional. We can effectively ignore these 6 extra dimensions because they're curled up on a very small scale, and as long as we don't get to extremely high energies, they're stable and they can be ignored. They don't have a real impact on the universe. So the simplest Braneworld models, which are motivated by M-theory, are 5-dimensional models, where we have an observable universe of 1 plus 3 dimensions. That's our ordinary universe that we experience. And then we have one large extra dimension. The other extra dimensions we neglect or ignore.
Why
Yeah.
only one large extra dimension?
Well, there are two answers to that. The one is that it's the easiest one to look at. Okay? And it turns out that even with that, it's very difficult to work out what's happening. So even just with one large extra dimension, we run into lots of problems, and we're still a long way from solving most of them. But the other answer to that is that if we take these M-theory solutions as a motivation, then there do exist solutions where one dimension is different from the other 6. There's not democracy amongst the dimensions. In fact, there are 3 classes of dimension. There's the large visible dimensions, including time. There's that's macroscopically large. There's the microscopically large extra dimension, and then there's the microscopically small extra dimensions. There are 3 different kinds of space dimensions, if you like, and then there's time. And we don't know why. We don't know why physics should make this choice. In fact, what you're saying actually raises a deeper question, which is if M-theory is correct and there really are 11 space-time dimensions, i.e. 10 space and 1 time, why is it that 3 of the space dimensions became big and the other 6 didn't? Or the other 7, rather. And that's an unanswered question. All we know is that there are solutions in which you do have this setup where you can actually neglect most of the extra dimensions, but one of them you can't neglect. So we start with that and we just say, okay, let's look at those kind of models and see what they tell us, while trying to see if someone can come up with an answer to the deeper question that you're raising. Yeah, Maureen.
Is there such a thing that it's easier to compactify on Calabi-Yau manifolds which are 6-dimensional, or does it not make a difference to the
Well, I think practically speaking, yes, these solutions are found because it's known that particular kinds of, as you say, Calabi-Yau manifolds with 6 dimensions are known, and so the solution was actually found partly on the basis of special properties which, you may well know that there's some very special properties attached to dimensions of spaces. So if you try to classify the topologies of all 3-dimensional spaces, that can be done, and has been done. But if you move up 1 extra dimension, there's just the number of topologies grows out of control. And so there are all sorts of results in differential geometry and algebraic geometry and topology, which tell us that spaces of different dimensions can have vastly different properties. There isn't just all dimensions aren't equal in some sense, but from a physics point of view, we still don't understand why 3 dimensions would have become large and the others not.
Sorry.
Yeah.
How did we stumble across the scale of this large extra dimension? I mean, how did we say that it was about a millimeter?
I'll show you, we're coming to that now. So that comes from experimental limits. The 1 millimeter is something that I'll discuss shortly. It's being narrowed down as experiments get more accurate. It's actually a bit less than a millimeter now. So the basic idea then is if we're going to take a simple phenomenology out of these kind of M-theory solutions, we're going to be looking at a 1 plus 3 plus 1 dimensional universe, neglecting any extra dimensions because they're so small. This extra dimension is large, not relative to the 3 observable dimensions, but relative to the Planck scale, or can be large relative to the Planck scale. So we have an effective phenomenological model. It's not an M-theory solution. The question was asked earlier, are these brane worlds actually M-theory? The answer is no. This brane world here is a supergravity solution. It's actually not quite it's a low-energy M-theory solution. But the ones that we work with in cosmology are phenomenological models. They're not strictly M-theory solutions. So we're going to be looking at models where our 3-dimensional universe with 1 time dimension and 3 space dimensions, and the matter attached to that universe without being able to move into the extra dimension has 1 extra dimension which can be large, where gravity is free to propagate. The basic idea, again, I emphasize, matter's on the brane, gravity is in the higher dimension, and the higher dimensional space-time is called the bulk, or it was a phrase that was coined at the beginning of the Braneworld papers. As I mentioned earlier, it also turns out that because this extra dimension can be large relative to the Planck length, it turns out that the fundamental scale of gravity, which I call M5, is not what we think it is, which is the Planck mass M4, which is 10 to the 19 GeV. It can be much less than that. So the reason that gravity seems to be so weak to us in this scenario is because gravity can leak into an extra dimension and become diluted. Gravity is not so weak. Okay? So this is a revolutionary idea that comes from a large extra dimension. So I'll run that by you again. Gravity seems to be very weak to us because we're stuck on a lower dimensional surface. But it's actually not so weak because gravity is able to leak into extra dimensions. And the true force of gravity is much stronger than we think it is because of that. Now, from now onwards, I'm going to choose a particular class of Braneworld models which are famous. You may have heard of them. Some of you will have heard of them, the Randle syndrome models. They are particularly appealing models. They're 5-dimensional Braneworld models, and what is particularly appealing about them is that they use some of the key ideas from general relativity to do with curvature in order to achieve the confinement of gravity on the brane so that we actually can reproduce the observations without having a theory that can't agree with anything that we observe. Now, what am I actually on about here? Well, let's just take a step back and suppose that we have our observable 4-dimensional world, the brane, and suppose we have an extra dimension which is completely flat, no curvature. If this extra dimension is infinite, then you can see that what's going to happen is gravity is just going to leak off to infinity. And so when we measure the gravitational potential from the force between 2 bodies in our laboratories, we're going to find that the gravitational potential is proportional to 1 over r squared. But actually, we know that when we do measure the force between particles in Cavendish-type experiments, it's not 1 over r squared, it's 1 over r. Okay, remember, this is the potential, not the force. So if we were to have an infinite flat extra dimension, we wouldn't be able to reproduce the observed universe because the attraction between particles would obey the wrong force law. So the basic reason being that gravity just leaks off your four-dimensional surface, and there's no four-dimensional gravity. There's no way of keeping gravity confined to the four-dimensional world so that it looks four-dimensional. Randle and Syndrome came along. Okay, so one solution to this, the traditional solution is to compactify this dimension. To say, okay, the dimension's not infinite, it's compact. It's like a circle rather than a straight line. And as long as you make the compact radius small enough, you can keep gravity looking effectively four-dimensional. That's the traditional Kaluza-Klein type solution. But Randle and Syndrome came along and said, okay, let's see if we can come up with a model where the extra dimension can still be infinite, but somehow we can keep gravity close to the brane. We can make gravity look four-dimensional at most energies. And their revolutionary idea was to say what we need in that extra dimension is curvature. We need a special kind of curvature that is going to, in a sense, confine gravity close to the wall, close to the brane. So here I've done a schematic here. You have this blue curve here represents the curvature in the extra dimension, so that it's strong close to the brane wall and tails off further away. And essentially the qualitative idea is that gravity tries to leak off the brane, but it's kind of bound by this high potential well. And so gravity, unless these gravitons have very high energy, they don't escape and they stay near to the brane. In other words, gravity looks effectively four-dimensional because it isn't allowed to leak off into the infinite extra dimension. This was the revolutionary idea that Randle and Syndrome came up with in 1999. And I'll explain that in more detail as we go along, just exactly how they do that. But this is the essential qualitative idea. And they're called warped brane worlds, just in the sense that we use the word warp for curvature. Curved brane worlds would be just as good, but warped sounds more dramatic, doesn't it? It sounds more exciting. So the key idea is you use a good old traditional Einstein notion of curvature in order to localize gravity so that it looks four-dimensional and can, in principle, therefore, reproduce the observations that we have in laboratories. And essentially what happens is, in order to curve the extra dimension, either you must put something in the extra dimension, but in these simple brane world models, we only have gravity in the extra dimension. We don't want to put matter in there. So the idea is that it's essentially the brane itself self-gravitates. It has its own gravitational force, which causes the curvature in the extra dimension. That's the old idea is the brane had no self-gravity.
Is there some basis why we believe extra dimensions are spatial as opposed to more time dimensions or some other type of dimension?
Yes, that's also a very good question. I should perhaps have mentioned that earlier. Thanks for pointing that out. Essentially, if you look at string theory, you start at string theory before supersymmetrizing it. String theory tells you that 25 spatial dimensions and one time dimension. It doesn't allow extra time dimensions, essentially because of Lorentz invariance. If you look at the dynamics of strings for bosonic strings, and you require Lorentz invariance at a local level, you basically come up with the only normalizable Lorentz invariant theory is in D equals 26 dimensions, one time like 25 space-like. We don't know why, but that's what the maths tells us. When you introduce supersymmetry, in other words, when you allow for fermionic strings, 26 gets cut down to 10, 1 plus 9. Then it turns out that there are 4 different superstring theories, and I'm sure you've heard about these. And it was discovered in the 90s as part of this revolution where branes were also discovered, that these 4 theories are related to each other by symmetry transformations, duality transformations they're called. And it was realized that, in fact, there's an overarching theory, M theory, of which the superstring theories are low energy limits. And the way in which these string theories can be mapped into each other entails the existence of an extra dimension, which is to do with the scale of the energy. And that was also space-like. So it all has to be space-like because of mathematical consistency. From a physical point of view, that's not a very satisfactory answer. But even if we didn't talk about extra dimensions, we could have asked the question, why do we have 1 time and 3 space dimensions? So even before string theory, That question that you ask is a question which remains unanswered. We don't know. You can construct Braneworld models with extra time dimensions. You don't have to be chained to string theory or M theory. You can say, okay, I'm going to just chuck in another time dimension. It can be done. But there are all sorts of problems with having more than one time, and I won't go into that. I don't really know much about them, but it can be done. Now, before we get into some of the basic features of the Randle syndrome models in terms of looking at the metric and the field equations, I should point out that there are actually two models that they introduced. First of all, they came up with the RS1 model, which has got two branes. Unfortunately, the one here is confusing because you'd think the RS1 has one brane, but that was their first model. It had two branes. And Randle syndrome 2 is a one-brane model with an infinite extra dimension. I did say the extra dimension is of the scale of about 1 millimeter, and you might ask me, now I'm saying it's infinite. I'll come back to you and explain what I mean by the millimeter later on. So they had these two possibilities. The first one was a bit like that one we'd seen before in 2 slides ago, where you have two branes, a visible brane and a shadow brane, and a large extra dimension connecting them. This was a completely revolutionary model where you only had one brane and an infinite extra dimension. This was completely new, never been seen before. This was semi-revolutionary in the sense that the extra dimension here is not flat, but also warped. So the extra dimension is warped in both cases. It's curved in both cases. But the one model is compact and the other is non-compact. What are the ingredients of these braneworlds? Well, the 5-dimensional space-time satisfies Einstein's equations. So you know what Einstein's equations are. In 4 dimensions, suppose I have 4-dimensional Einstein gravity with no matter, the equations would be g mu nu plus lambda 4 g mu nu is 0. I might have a vacuum energy, but no matter, so there's no t mu nu on the right-hand side. That would be 4-dimensional gravity with no matter. So now, if we go to the 5D case, where we're saying that in the bulk there's no matter, at most there could be a vacuum, we then have a 5-dimensional Einstein tensor. I'm using uppercase indices because they go from 0, 1, 2, 3, and 4, not just up to 3. So they're different from the Greek letters. I will have a 5-dimensional vacuum energy at most possible. And then, of course, I've got a 5-dimensional metric here. Equals 0. So we keep Einstein's basic equations, and we've got no matter in the bulk space-time, so there's no energy-momentum tensor there. But we do actually have this vacuum energy in the bulk. Now, you know about dark energy, and the cosmological constant is a special case. And in the 4-dimensional universe, the cosmological constant we're talking about is positive. That's what's causing the universe to accelerate. If you think about it a bit, if I had a positive cosmological constant in 5 dimensions, it would have the effect of actually accelerating the leakage of gravity off the brane. What we need is the opposite effect. We need a negative cosmological constant to keep gravity confined onto the brane. So it turns out that this lambda 5 here, this 5-dimensional vacuum energy, must be negative. Okay? The brane has a tension. If I use lowercase lambda for the tension, this is like a vacuum energy intrinsic to the brane itself. It's its own self-gravity. And in fact, it's because of this tension that you get that negative cosmological constant. So if I have the one brane model, for example, and I say that brane has a positive vacuum energy lambda, then necessarily that will give me a negative 5-dimensional capital lambda. This is what the field equations tell you. In the 2-brane case, in order to keep the 2-brane models stable, one of the shadow brane has to have a negative brane tension, equal and opposite to the visible brane.
Sorry.
Yeah.
Is the brane tension somehow coordinate dependent?
No.
Okay, so then I'm totally lost. I don't understand. Okay, so let's take a step back from the Einstein's equations.
Mm-hmm.
If I was supposed to, if I put in the energy stress tensor, are you now telling me that it can be 5-dimensional? So therefore we have to have some sort of notion of what the energy stress tensor is in this extra dimension.
Okay, this is not the actual field equations on the brane. This was just, I was saying, you know the 4D case, the 5D case is exactly the same, just one extra index. I'm not sure what your question is, though. Were you saying...
So if you complete the Einstein's field equations and put in the energy stress tensor...
So actually what happens... Okay, we're jumping ahead here, but we may as well answer it. What actually happens on the brane... This is in the bulk. On the brane you get what looks like Einstein's field equations. And then you get extra terms, correction terms. And these come from the extra dimension.
So what do they represent? I mean, we know what the energy stress tensor is supposed to be, but what...
Okay, so this pi here is a function of the energy momentum tensor. It's actually quadratic in the energy momentum tensor. I'll come to this a bit later, but since you've asked, let me jump ahead a bit. And this is actually a high energy term. So in the early universe, this term begins to dominate over that term. And it brings changes to what you would expect from Einstein's theory. And this is not surprising, because the higher the energy, the more the deviation from general relativity. This term here is a 5-dimensional graviton term. So gravity is 5-dimensional. The graviton is a 5-dimensional particle. It has extra degrees of freedom, not just the 2 polarizations we know of from the 4-dimensional graviton. And some of those degrees of freedom make themselves felt on the brane. So this is the kind of direct imprint on the brane of the extra-dimensional gravity field. So these are the terms which bring in the deviations. Okay. We'll come back to them a little bit later as well. There is one other ingredient which we inherit from M-theory, and this is this notion of mirror symmetry. If you ask, say, in the one brane model, what's on the other side of the brane, the answer is it's an exact copy of what's on this side of the brane. So we have a mirror symmetry. The fancy word for it is Z2 symmetry. It's something that comes out of string theory. And it helps us to make the models more simple. So we're happy to inherit this idea from string theory. Similarly, in the two-brane model, what is other side of the branes is just a copy of what is in this side. There's complete mirror symmetry about each brane. Okay. Now, I've tried to sort of identify for you the basic ingredients that go into these Braneworld models. But at some stage, I have to stop waving my hands and actually show you some equations so that you can see how these things might start fitting together. So the field equations in the bulk, as I'd already written down, are just Einstein's equations in 5 dimensions with a cosmological constant, which happens to be negative, a vacuum energy which is negative. You might say, why is the vacuum energy not positive? Well, if you try with a positive vacuum energy, gravity leaks off the brane even faster than it would for a flat extra dimension. So it just doesn't work. You have to have a negative cosmological constant to keep gravity confined close to the brane. The Randle syndrome solution, then, to these equations was given by this very simple metric. So there's the extra dimension, dy squared. You can see there's a positive dy squared because it's space-like. The extra dimension is space-like. I've got the two-brane model here and the one-brane model here. The warp factor is just, this warp factor here is this exponential. So if you drew that warp factor, if you just plotted it, it would look like this. Because of that absolute value there, which is the mirror symmetry, this is e to the minus 2 mod y over L. So this you can think of as the kind of volcano potential around the brane, which is keeping gravity confined. So the gravity is kept close to the brane and it can't penetrate this potential except if at very high energies. When the energy gets high enough, gravity just zips through there and becomes 5-dimensional, and the universe, the 4D universe, is very different from what Einstein's theory would predict. This eta mu nu here is just your standard Mankowski metric. So whenever y is constant, either in the one brane case y equals 0 is the brane, so this term becomes 1. In the two brane case, it's 1 at the visible brane, and it's e to the some constant, so it's just a constant number here at the shadow brane. So the branes are Minkowski spacetimes. If I set y equals constant, the metric is the metric of Minkowski. Now there's a slight subtlety here, because the brane has a vacuum energy or a tension, which I've called lambda. We know from Einstein's theory that if you put any kind of energy into a Minkowski spacetime, it will immediately generate an Einstein curvature, which is non-zero, and so the metric will no longer be flat. So how do I manage to have this self-gravity in the form of brane tension at the same time as I have a Minkowski geometry? And the essential idea is that the positive vacuum energy on the brane is cancelled by the negative vacuum energy in the bulk. They kind of cancel each other. And that involves a fine-tuning. There's a fine-tuning there. If you break the fine-tuning, then the brane is no longer Minkowski. It becomes a de Sitter brane, that exponentially expanding brane in one case, or an anti-de Sitter brane, the opposite case that you may have heard about. Yeah, Noreen.
So you never defined the lambda brane tension. How does it relate to the four-dimensional cosmological constant and the five-dimensional cosmological?
Okay, so the four-dimensional cosmological constant in these models is 0. And in fact, the general expression is the following. This is a half lambda 5 plus 8 pi g lambda. Or the 8 pi g I can write as 8 pi over the four-dimensional Planck mass squared. So this is the actual relationship. I think I might have a... I'm not sure if that's a 4 or 8, but anyway, it's up to a possible number here. This is correct. So if this is 0, you get the Randle syndrome solution. If I have a little bit too much brane tension, I'm going to get a positive lambda 4, and so I'll get an expanding de Sitter brane. If I have too little brane tension, then it'll swing to the negative, and I'll get a negative lambda 4, an anti-de Sitter brane. So there is this fine-tuning, but it's really a battle between the negative bulk cosmological constant and the positive brane tension in terms of the one brane model. Two brane model is slightly different. I mean, it's got a negative tension on that brane, but the two are held together by a similar kind of fine-tuning. The fine-tuning equation here has an extra exponential factor in it, which makes it slightly different, but still it's the same basic idea. Yeah, Jeff.
So phenomenologically, is this why you pick an five-dimensional anti-de Sitter bulk? Because if we live in a positive tension brane, and you need something to cancel it out to give you lambda equals 0 on the brane.
If we have a one brane model, then it turns out that this term here is proportional to the brane tension. So if you have negative brane tension, you have the wrong sign. Gravity becomes repulsive instead of attractive. Two brane models are a bit different and more complicated, but certainly in the one brane case, you must have that positive brane tension, otherwise gravity is not attractive at low energies. And once you have that, then you've got to have a negative lambda from this fine-tuning here. And in a sense, really, as I said before, it's the tension of the brane that generates the cosmological constant in the bulk. But that was a bit of a fudge, because there is this fine-tuning here, that you want the cosmological constant on the brane to be 0. At least for simple models, we'll have it 0.
Just a general question. What does it mean from the quantum field theory side of things if you have a negative vacuum energy?
Well, the quantum field theorists that I know tell me that there's no problem with negative energies, negative vacuum energy.
Linda Kalash and people wrote a paper after the paper came out that said you can't live on a negative tension brane. so the ecmagnetic stuff went wrong, and then another paper came out by Mtheory and people that said, of course you can. And so,
Yes, as soon as you've got more than one brane, you can actually live. The visible brane can have a negative tension. It's a bit subtle. And you've got in the one brane scenario, you do, at least in simple cases, you do need this to be positive. But Noreen's asking a more fundamental question. I mean, yesterday I did a back-of-the-envelope calculation to estimate the dark energy and showed it should be determined by the Planck energy. And there I just assumed that it was positive. The 0-point energy of harmonic oscillators is positive, not negative. So there is a subtlety involved as how you can have a negative vacuum energy in 5 dimensions. But apparently that's compatible with quantum field theory. I can't claim to know why. That's a good question.
Sorry,
Yeah.
I'm not too clear on your exponent that you've got here, the sort of potential that you define to restrict your gravitational interaction in the extra dimension. Is that phenomenological?
No, it's a bit of a cheat, because this isn't really a potential. That's just a metric function. It's a conformal factor outside the 4-dimensional part of the metric. It turns out when we perturb this, which I'll describe shortly, to look at gravitational perturbations, the weak field limit, it turns out that we get an effective volcano potential around the brane, which actually looks like this. It has these exponential fall-offs, and then it goes to minus infinity. There's a Dirac delta function at the brane. And that's actually the volcano, because it looks like a pipe of a volcano going down into the depths. So this potential comes from the perturbing that scenario, and the shape of it is determined by this warp factor. This isn't really the potential, so I was doing a bit of a cheat there. That's well spotted by you. It's not actually a potential. This is an exact solution of these field equations, with the boundary conditions having a brane either in one case or the 2 boundary conditions in this case. So it's an exact solution of those field equations with the mirror symmetry that I spoke about. You put that all together, you find that this is exactly a solution. So it's not phenomenal. It's not postulated. It's just a solution. Okay, so please carry on interrupting me as much as you like, because I think that's much better than I just carry on talking. But I want to now take one step further and say, okay, what I've described up to now is the simplest 5-dimensional scenario where the observable brane is a plain old flat Mankowski spacetime. But we know that if we want to do cosmology or any kind of gravitational experimentation or observation, we need to introduce some perturbation or radical change to the Mankowski brane. So the first thing we'll do, eventually we want a Friedmann-Robertson-Walker brane, but before we do that, let's suppose we just put a particle on the brane. So I'm going to put a mass on this Mankowski brane. It's going to bring its gravitational field, and we'd like to have a look at the potential. Remember I was telling you earlier that the gravitational potential, a truly 5-dimensional gravitational potential will go like 1 over r squared. A truly 4-dimensional one will go like 1 over r. So if the Randle syndrome models are going to be successful, we should find it's 1 over r plus a correction. And the correction will have to be small so as to be compatible with our observed world. So that's the idea. That's what we need to try and do. In order to do that, we have to think a bit about what this 5-dimensional gravity is in relation to 4-dimensional observations. So the first thing you can say is a graviton, whether it's 4-dimensional or 5-dimensional, has a null energy momentum vector. It's a massless particle. But if I have an observable universe which has 4 dimensions and a true universe which is 5-dimensional, I have a slight subtlety there, because from the point of view of the 5-dimensional bulk spacetime, the graviton is massless. But from the point of view of the observers who are 4-dimensional, it's not massless. How does that work? Well, it's not difficult, actually. You start off by, I've got these superscripts in brackets, the 5, just meaning 5-dimensional quantities, as I used over here for the metric and the Einstein tensor. as 5-dimensional vectors, the momentum vector for gravitons is null. In other words, the graviton is massless in 5 dimensions. It's truly a massless particle as a 5-dimensional particle. So let's look at this scenario. Here's the brane, where we're stuck as observers. This is the momentum vector of a 5-dimensional graviton. It's tangent to the 5-dimensional light cone, which I haven't drawn in there. But I can project that vector onto the brane. Here's the normal to the brane. I can project that vector onto the brane, and this projection here is what I feel on the brane from this vector. So because I'm stuck to the brane, all I can feel from this vector is its projection onto the brane. It's kind of shadow onto the brane. And it's not hard to see that this 4-dimensional vector, which is the projection of that, is time-like. It's not null. You can see immediately from my diagram it's a time-like vector. Remember, time goes up, space goes along, and down here, this is a null vector in 5 dimensions. I project onto the brane. You can see that must be time-like. It's inside the 5-dimensional light cone. It's a time-like vector. In other words, it has a mass. So the effect of this truly massive particle, as measured on the brane, is as if it were a massive particle. And the mass just happens to be a measure of the angle between the 5-dimensional graviton momentum and the normal to the brane. So this is an exercise that you might like to try. It's not difficult. Take this equation here and work out what this is in terms of a projection and see if you can show that it's a time-like. You can see it's time-like, but just see if you can work out the mass explicitly as I have it there. So this really is the fundamental idea. And essentially what we're saying is from another point of view, I can say it in the following way. The 4-dimensional graviton, if the universe is 4-dimensional as we normally believe in Einstein's theory, we know gravitational waves have 2 polarizations. Right? So there are 2 degrees of freedom to the 4-dimensional graviton. The 5-dimensional graviton has 5 polarizations. It has 5 degrees of freedom. This can be worked out mathematically. For each dimension, the number of degrees of freedom goes higher and higher and higher. But the 5D graviton has 5 degrees of freedom. And essentially, what that means is that if we're stuck on a 4-dimensional surface, we can feel some of those degrees of freedom as if they were massive particles. That's the basic idea. Because from our point of view, there's only 2 degrees of freedom in massless particles. So we can't capture all the properties of the 5-dimensional graviton if it were to be only felt as a massless particle. It has to have an effective mass on the brane. Now, for historical reasons, this mass parameter m is associated with what's known as a Kaluza-Klein mode of the graviton. Okay, I've just given you one single graviton moving in a particular direction there, but gravitational disturbances involve a whole family of gravitational wave modes, and each of them will have effective masses, and so they will add up in different ways, and you get on the brane different modes of the 5-dimensional graviton. And for historical reasons, these are called Kaluza-Klein modes. And we say they're massive because they have an effective mass on the brane, even though they come from the massless graviton. It takes a bit of getting used to this notion, but this is essentially how the 5-dimensional gravity makes itself felt on the brane. Now, those of you, and I'm assuming it's many of you, who have done the weak field approximation in general relativity, should recognize some of the basic steps that I'm going to go through now. In the weak field approximation in general relativity, you would start with the Mankowski metric, and then you would introduce a perturbation. You would add a small bit to the Mankowski metric, this h mu nu. And then you look at Einstein's equations, and eventually you work out that h mu nu satisfies the wave equation. And that's gravitational waves on a Mankowski background. So we're just going to do exactly the same thing, except with an extra dimension, to see what happens because of this extra dimension. So we start with the basic Randle syndrome solution. There's the Mankowski metric of the brane, there's the warp factor, and there's the extra dimension. if we put a particle on the brane which is small enough so that it doesn't completely radically alter the geometry, it just disturbs it a little bit, that's going to make a shift from eta to eta plus h, where h is small, a set of small quantities. Now, you might remember, those of you who've done this, the others will just have to take my word for it. In order to get to this wave equation here, we impose gauge conditions, and we take the spatial part h mu 0, 0. We kill all the time components of the h, and then for the space components that are left, we require them to have no divergence and no trace. Now we do exactly the same thing, but with one extra dimension. We've already imposed this condition here because we've got h mu 4 is 0. Okay, I've got no h perturbation on the y there. So just as I would in 4 dimensions kill off the time components of the h here, I kill off the y components. I could use a y here instead of a 4, it might be better. H mu y is 0. And then the remaining components must be trace-free and divergence-free. But of course, they're extra components now. I've got 4x4 matrix rather than a 3x3 matrix because I've got one extra dimension. But apart from that, I'm doing exactly the same as I would in a standard textbook treatment of the weak field limit of Einstein's equations. Okay? Then what you do is you go to the field equations, which I've just pushed up on the board here. I'll bring it back again. Just go to these field equations here, and you plug the perturbed metric into the field equations and linearize. Takes a bit of a while, but you end up then with this equation here. That didn't come out too well. E to the 2y over L, h double dot plus k squared h. K is just the Fourier mode there, so this would be from the Laplacian. Equals h double prime minus 4 over L h prime. Now, that's just really the 5-dimensional version of this equation. And the solution of it is a bit more complicated than it is in 4 dimensions. You can see immediately that this 5-dimensional wave equation is separable. I can separate into time and y dependence. And that's important because the modes that I'm going to separate into are going to have a mass, and that mass is going to be the effective mass of the graviton degrees of freedom. What about the boundary conditions? Well, you would require that the y derivative of h, which is just the amplitude of this tensor, should vanish at each of the branes. If there's only one brane, there's just one boundary condition. But if there are 2 branes, the boundary condition must hold at each brane. So if you do that, it's not important. The details of the solution are not important, but I'll just show them to you. The time dependence is quite straightforward. It's just exponential plus or minus it times this modified wave number here, where instead of just a k, we get root k squared plus m squared, where m is the separation parameter, which turns out to be the mass, effective mass of 5D graviton modes. And this solution is true for all values of m. The y dependence separates out into 2 pieces. You have a 0 mode, which is the massless mode. Okay, so there is the massless mode, if you like, is the case where the 5-dimensional graviton momentum is actually in the brane. So the projection of that is already equal to itself on the brane. And that's the massless mode, if you like, the 0 mode. The solution there is very easy. It's just a constant. But the massive modes turn out to be given by Bessel functions of order 2, which involve the warp factor and the mass parameter m. So we have a whole tower of massive modes of the 5-dimensional graviton on the brane as the way of as the effect on the brane of the 5-dimensional gravitational field. In the RS1 model, where you have two boundary conditions on these Bessel functions, you find that only specific values of m solve those boundary conditions. So you get a discrete tower of modes. So we get, in the RS1 case, only particular values of m would be allowed. As m equals 0, and the first mode, the second mode, and so on. An infinite tower of discrete modes. That's the two-brane model. But for the one-brane model, you just get a continuum of modes. There's a complete continuum. There's no discretization because the extra dimension is infinite. Now, what you can then do is you can take these solutions and you can work out the gravitational potential. So these solutions, you go back to the metric and see what the form of the metric is. Remember, yesterday I was talking about the perturbation of the metric where I had this term 1 plus 2 phi dt squared, and that phi is the gravitational potential. Essentially, you go back and look at the G0 component of the metric to work out what the gravitational potential is. I'm not going to do it here. It's a bit messy technically, but that's essentially what you do. And what you find is that the gravitational potential is proportional to 1 over r, which is our standard four-dimensional gravitational potential, that 1 there. And then the lowest order correction term is 2L squared over 3R squared. That's a dimensionless quantity. So the correction term is a 1 over R cubed term. And here we see exactly the difference contribution of the modes of the five-dimensional graviton. This is the massless mode. It's the one which gives me four-dimensional gravity. The massive modes add up to give me this correction to four-dimensional gravity. Okay, so this is the real fundamental feature that comes out of this analysis. So this is the key idea. The massive modes of that five-dimensional gravitational field add up to introduce corrections to Newton's law in this case, if you like. Now, it turns out that from a technological point of view...
Quick question. In all classes of those models, do you end up with a minus sign, a reduction in the strength, a minus 2/3?
In these classes of models, yes, because essentially gravity is leaking off the brane. Okay, you can... Yes, I think probably all classes should have a minus. I don't know of any with pluses. Yes, I think they're always minus. How are you going to test this experimentally? Now, that turns out to actually be quite a challenge technologically because electrostatic and other chemical forces are much stronger than gravitational forces. Trying to test the gravitational interaction between particles on smaller and smaller scales becomes very difficult. And it was only after I suppose, maybe the late 90s, but actually even a bit beyond that the technology was developed to start probing Newton's law down to distances of order 1 millimeter. And currently, I think the limits now are that Newton's law holds phi is proportional to 1 over r without any observable difference down to, I think it's a distance of about 0.2 millimeters. It may be 0.1 now. And this involves real high-tech experimentation, the state of the art. Very difficult to do this, to screen off all the other forces and actually detect the gravitational force. But that's being done and it's getting better. And as the experiments get better and as this number gets smaller and smaller, it's going to make the size, if you like, the effective size of the extra dimension smaller and smaller. But currently, we're down to 0.2 of a millimeter. And that means if you go back to the expression I had on a previous slide and work out what the value of the brane tension is, the brane tension has to be at least 1 TeV to the 4. So the critical energy scale, which is implied by these tabletop experiments in the Randle syndrome models currently, is just above the electroweak scale. So what we're saying is that the changes to Einstein's theory have to happen at energies higher than the electroweak scale. If they happen lower than the electroweak scale in these models, we would already have seen the changes in tabletop experiments. I should pause now just to make a point here. It's a bit confusing to have in the Randle syndrome 2 case, the extra dimension y is infinite, so it goes from 0 to infinity. But the curvature scale, remember I had the expression lambda 5 is minus 6 over L squared. If you worked out the curvature tensor of the bulk, you would find it's minus 1 over L squared 5G AC 5G BD minus 5G AD 5G BC. In the square brackets is the typical expression for a constant curvature metric space, and the factor out there is the curvature scale, and L itself is called the curvature radius. So this really is the effective size of the extra dimension. The actual size is infinite, but when you work out the volume integrals where you have d 5x roots minus 5g some quantity, you can see the warp factor is coming in there. And essentially, it means that the effective volume of the extra dimension is determined by L. The effective volume of the extra dimension is not infinite. As an exercise, you might like to show that the volume is less than infinity. Even though the actual length in terms of the y coordinate is infinite, the volume of the extra dimension is finite. So this curvature radius is the effective size of the extra dimension. And that's why I was saying that the large extra dimension has to be less than a millimeter. In fact, there are models in which the extra dimension is infinite, but effectively it is of the order of a millimeter at most. Okay, so I haven't got much time left, and I realize I've thrown a lot of ideas at you, but if you can just take away some of them, that'll be good. You can appreciate that there are a lot of technicalities in here, and trying to sort of avoid most of them, and keeping those which are crucial is the trick, and I don't know if I'm succeeding, but anyway. I'll end off by a few slides to discuss the next development. So running backwards again, just to repeat what I've done, I've gone through some of the basic ideas with hand wavings, and I've taken you into the Randle syndrome models, which are based on Mankowski brains. And then we took the next step, which was to put a particle on there to see what happens when you introduce little wiggles to the Mankowski setup. Of course, the following step, the one that we really need to take, is to have a Robertson-Walker brain so we can do cosmology and see what the extra dimensions are doing for us. So how does that work? Well, without going into all the details, essentially what happens is the following. You can get a Friedmann-Robertson-Walker brain in the 5-dimensional bulk, which has the following properties. You've got a negative cosmological constant, lambda 5, exactly as in the previous simple models. But in addition, you have a black hole in the bulk. So this is a 5-dimensional black hole with mass c. I'll just call it c. And at the same time, the brain is moving away from the black hole. The velocity that it's moving with is determined exactly by the Hubble rate. And so in these models, what we can say is the following, that the expansion of the universe can be thought of as due to the motion of our observable world through the 5th dimension. So we move through the 5th dimension with the velocity which exactly determines the Hubble rate. It's not strictly true that that's fundamental, because I can always make the brain come to a rest by choosing different coordinates. But it's a nice way of thinking of the expansion of the universe. It's not real expansion, it's just because we're moving through the 5th dimension. And as we move through the 5th dimension, the gravitational field changes, and so that has a real effect on the brain. I've written the metric down here for this setup. It's not really important. I just want you to see the structure of it. It's a bit like a Schwarzschild metric, minus f of r dt squared plus dr squared over f. That's exactly the structure of a Schwarzschild metric in the time radius sector of the metric. But the f is a bit different. First of all, it's got a k there, which this k is the curvature of the Friedmann brain. It might be 0, it might be +1, it might be -1. Then there's an r squared over L squared. So this 1 over L squared is the cosmological constant term, the lambda 5. And then here the c over r squared, that's just the 1 over r squared potential from 5 dimensions. So this is the potential due to the 5-dimensional black hole. It's truly 5-dimensional. The rest of the metric is the radius coordinate on the brane, little r, and then the angular coordinates theta and phi on the brane. And you can see that if I set r to be a function, to be equal to a, some function of t, this dr squared now becomes proportional to a dt squared. So both of these first two terms just become something dt squared, and you can see that with that being an a squared, that's a Robertson-Walker metric. Okay? So as an exercise, you might like to just show that by setting r as a function a of t, I get a Robertson-Walker metric. So show that r equals a of t gives a Friedmann-Robertson-Walker metric minus dt squared plus a squared of t dr squared over 1 minus kr squared plus r squared d omega squared. It's quite straightforward to show that, but it's worth just doing it if you can't see it immediately. Yeah.
I have two questions. First of all, where the black hole has matter in it, and gravitation, and the brane has all the matter that we feel on it, why would you have be attracted to the black hole? Why would you move away?
Because of the negative cosmological constant.
Stronger than. Okay. And secondly, would you interpret the black hole?
Sorry, can I just come back? If the expansion rate of h is negative, if you collapse it, then you're actually falling into the black hole. So it's not quite true what I said. If you're expanding, you're moving away. Yeah. Sorry. Second question?
Second question was the black hole would then be interpreted as a different kind of brane, like a zero brane, or because you said all the just potential brane.
Yes, that's a good question. I mean, I should also say that in the case where k equals 0, that diagram of mine is a bit misleading. I should really have a black brane in the case k equals 0. Not a sphere. The diagram really corresponds to the case k equals 1. But yes, essentially what you're saying is, where did that black hole come from? Because there can't be matter in the extra dimension. And normally we think of black holes as being created by the collapse of matter. So this is not a black hole created by the collapse of matter. Either it emerges in the creation of the universe from some instanton. So just like you have four-dimensional instantons which account for the creation of the universe in four-dimensional theories, so too you can have five-dimensional instantons. And some of those instantons can be set up so that a black hole emerges in the bulk at the same time as the brane begins to move away from it. Or it can happen that you can have high energy. If you have in the very early universe very high energy collisions between particles generating five-dimensional gravitational waves, and those waves going into the bulk and creating a black hole. The black hole emerges from gravitational waves. That's the other possibility. Okay? So that,
Again, that was K was the 3 curvature.
yes, K is the 3 curvature. So K tells us about the curvature of the surfaces R equals A of T.
So how does k equal 0 give you a black brane?
Well, it just says that the topology of it's a bit like the topology of the Big Bang. I kind of draw it. I've drawn this here as a plane. I don't really know what it's going to look like. It's a bit like, but it's certainly not a sphere when k equals 0. Okay, it's not a point particle. So the k equals 0 case, the surfaces have plane symmetry. The k equals +1 case, the surfaces have spherical symmetry. So when you take the spherical symmetry surface down to the limit at the center, you get this black hole that I've drawn there. But when you take the plane symmetry things down to the limit, you don't get anything. You just get another plane.
What's the dimension of the brain, though?
Dimension of the brain?
Of the black brain? Because I live in a 5-dimensional.
It's a 4-dimensional.
So it's 4-dimensional.
Well, it's a 5-dimensional singularity. Yeah, got to be a bit careful.
But
So it's got to. You see, I should actually take the Fifth Amendment here and say that actually there's a horizon. Okay. In the case that I've drawn there, the horizon is a sphere like this. And inside the horizon, you can go and look at that, but I'm not interested. I'm just going to be outside the horizon. So inside the horizon, there is that singularity. The horizon is spherical in the one I've drawn there, but in the k equals 0 case, the horizon is a plane. It's an infinite plane. And what's behind the horizon, well, that's another issue. And the nature of the singularity, you can't really draw it. Oops.
How much of what happens on the FRW brain is dependent on the geometry of the black hole? Well, never mind the geometry, because obviously it's a black hole. So I have mass, charge, and there's
Yes.
angular momentum of the black hole.
Yes.
How much of what happens in the Robertson-Walker brain depends on that?
Okay.
Sorry, can I just make one more?
Yeah.
I'll forget about it. Because in 5 dimensions, Birkhoff's theorem doesn't hold anymore. So you're not necessarily going to get a spherical brain as the only solution. You can get a ring-like brain, and this was Real and Roberto Amparo. I'm sure that you get these ring-like objects that also have all the properties of a black hole, except that Birkhoff's theorem doesn't seem to hold in 5D anymore in this kind of
There's a modified Birkhoff theorem which holds for stationary static box. There's a stationary, but it's also not asymptotically flat.
Right.
But your first question, which is a bit easier to deal with, is answered in the following way, that the gravitational field of the black hole is felt on the brain, but it's felt in a way which dies off because the brain is moving further and further away. So the gravitational effect of the black hole on the brain should be something which is falling off with expansion. And maybe the easiest way to answer is just to show the Friedman equation. The Friedman equation picks up an extra term. There C is the mass parameter of the bulk black hole. C over A to the 4. So you can see as the universe expands, this is growing bigger and bigger, so this term is getting smaller and smaller. As you further and further away from the black hole, its influence on you is weaker and weaker. But as you go back in time, the influence of the black hole on the expansion rate is stronger. So that's the Coulomb effect of the 5-dimensional black hole being felt on the brain. It's not gravitational waves, but it's the Coulomb effect. Yeah.
What happens to the brain, the expansion thing, you put the R as a function of T in by hand, don't you? Or does it come from, on the previous slide, R?
Yes, it's slightly coordinate dependent. Those are useful coordinates to use in which the brain actually moves at the speed given by the Hubble rate. But you can choose other coordinates in which the brain is stationary.
And then you don't get any Hubble expansion.
You do, but it's reinterpreted in a different way. Those coordinates are a nice way of interpreting the expansion. But the actual expansion is real. This Friedman equation holds in any coordinate system. Whichever coordinates I choose for the bulk, the measured expansion rate on the brain is always equal to this. So I can use, it's just like in GR, I can write down the Robertson-Walker metric and the natural coordinates that I have here, or I can choose some horrible coordinates in which it will take me sort of a month to realize it's a Robertson-Walker metric.
But then I don't think I understand why
But in both cases, the Friedman equation is the same.
But so why is square root once again? The AS5 curvature doesn't make it away from black hole, it just makes it not to get and not to fall in it.
Well, let's think. My answer for your earlier question was actually wrong, because the movement is not real. The movement is a coordinate effect. Because I can bring that brain to a stop by coordinates. You know from GR that velocities are relative. So I can always use a Lorentz boost to get rid of a velocity. And I can do that, and I can choose other coordinates in which the brain comes to a rest. They're more artificial coordinates, not so easy to see what's happening in those coordinates.
But you say that even so you take these kind of coordinates in which the brain just stays in a different space,
does. I mean, it's just more difficult to see why it happens in different coordinates. Those coordinates are useful because it's an easy way of seeing how it happens. If I choose different coordinates, then it's difficult to see why the effect of the black hole on the brain is diminishing with time.
Itself collapses after a while.
Sorry?
ADS5 itself, it expands and it collapses, right?
ADS5? No, it's static. ADS5 is static. Just like DS5. DS4 is also static. De Sitter, that point was made when I gave my first inflation lecture. De Sitter space-time is static. You can choose particular slicings in which expand or collapse. But ADS5 as a space-time is static. I mean, this is a tricky point. How do you... I can't really go into it, because I'd have to show you a different set of coordinates and show you in detail how the effect of the black hole diminishes on the brain without having this simple picture of movement. But these are the easiest coordinates in which to interpret things. So I've run out of time. Let me stop here, although I've got a few more slides. It doesn't matter. Let's just stop with this Friedman equation. I wanted you just to notice the two extra terms that we get, which we don't have in GR. The first is that high energy term I mentioned earlier. Lambda is that brain tension, which we know is at least the electroweak scale or higher. So when the energy of the universe gets much bigger than the electroweak scale, this term dominates over the one here, and we get a completely different behavior in the early universe. Also in the early universe, this term here could be important when A is small. This is the term due to the 5-dimensional gravitational field of the black hole. So this is the massive modes of the 5-dimensional graviton. These are the sort of Kaluza-Klein modes, if you like. This is the high energy term. The other terms are standard terms. They're just exactly what you'd get in GR. The two key terms are the correction terms from extra dimensions. And I'll end off by saying the conservation equation is the same. I don't have time to go through the solutions of Friedman's equation, how they change from GR. But those of you interested in a few extra exercises could try to derive those last two boxes. I'll have to stop there.